So we'll introduce some shorthand notation for displaying the states. So we'll be using this one. Sometimes in certain applications 0 and 1 are used. We'll be using the plus and minus one. So in that sense, identity operator for spin-half systems will be written something like this. Projection operators plus minus eigencats, summation of eigencats basically with their respective eigenvalues. Sorry, just summation. And now if there is an operator A, we know that can be represented by this respective eigenvalues and the projection operator, this or something like this. Then operator will be from this we can this is how we so this is the respective eigenvalue of spin z states plus h bar by 2 and minus h bar by 2, and this is something that we are going to sum, right? In similar way, spin z operator and operated on plus minus states provides me with these are spin z eigenstates with this eigenvalue, spin half h bar by 2. Okay, so you can try to these are some things don't overlap. The inner product is 0. They are normalized states. This is one. Another natural question is that can I go from state plus to state minus, or some state minus to some state plus? So the answer is yes. Can try and see. So if I have something like this, if this is an operator which acts on state plus, now how can I write this? As we know that this is 0, this is going to be 0. So we can try something else. If I operate this in negative state, this will give me 1, it will be plus. So this operator acting on this state changes it to the positive state. If I reverse this now, and operate this on plus state, this positive and positive bracket will give you 1 and come to negative state. So we propose two operators. Yeah. So this will raise spin component by 1 unit. This will lower the spin component by 1 unit of h bar. And we should notice that so notice that these raising and lowering operators, they are not Hermitian. Why do we care? Because non-Hermitian operators will not have real eigenvalues. So in a way it is not observable. Okay, fine. So the next step is that how we are going to represent this spin eigenstates or angular momentum states in a way. So we have defined this plus and minus. So in terms of matrix representations, it is generally customary to have the highest value of the whatever observable or eigenvalue or whatever the values are. The highest are generally denoted as first, and the rest of the entries are zero. So highest angular momentum value will be the first entry. So this will correspond to the highest, which in our case is plus h bar by 2. Then this is minus h bar by 2. This is how we will represent them. This is two-dimensional. Remember, this two-dimensional complex vector space. We are trying to represent them there. So based on this, right? So this is the outer product. So this will be a column. This will be a row. So we are going to write this. This is 1 0. So if we write down the entire matrix, what would it look like? Look like this. So this is the spin Z operator, right? This is the Pauli matrices. So Pauli matrices are written like this. Their trace is 0. So how do we find the spin X vector? So we know that when there is a pure spin X and if this is subjected to Z filter, there is pure SX field which is subjected to Z filter. We know that we get such kind of result when there is 50% of both the means present. So, okay. So we know that the overlap of states probability entity. This is half, 50%. So what we can demand is this, that similarly this is just a relative phase, later that what this will continue. But this is how we can write 50% of squareness, you get 50% of plus and 50% of plus minus, same goes there. So how do we write the SX operator? We know that multiply this with itself, first complex conjugate, so what will happen? 1 by root 2 positive multiplied with itself, so this will be 1 by root 2 plus plus as well. this is nothing but the identity operator. So this both will cancel and will be 0. These two will cancel. So I will left with this part. What will that be? This part will also cancel. Just multiplied here with this term itself. So this gives me this with itself, this with itself, plus and plus. Then there are cross terms, positive, negative. This, this. Then there is this part, this part. Then gives me positive part. We can note here that this is a Hermitian operator. So I take this negative to positive, reverse this. This also becomes negative. This is same. This term is here. This term is same. This is a Hermitian operator. Remember that Hermitian operators have real eigenvalue. So it's obvious that this should be an Hermitian operator, and similarly we can mark this. What we get try to do this. Let's see. Yeah, I will see. And you can also notice that this is same look at the overlap of two states in Y. Interested in finding the overlap of spin x plus state. How much overlap is there with the spin y plus or minus states? Right. So this is usually 1 by root 2, this 1 by root 2 as 1. This will be so if this is pi by 2, e power I pi by 2 gives me cos pi by 2 plus I sin pi by 2. This will be if I take this is basically rotation. And even if we have given rotation to the states, this probability magnitude is not changing. This is obvious and expected. States are rotated in their two-dimensional vector space. This answers should not change. The probability should not change. So suppose we fix this pi by 2, this is 0, then what will the this x operator will look like? Do the matrix form. Similarly, if we first part will be 0, this will be a complex entry. In Y operator as well, and we know that Z operator is so we have identified the spin operators which act on the spin Z states or the linear combinations. So we have divided this operators in matrix forms which are very related to the Pauli matrices. Notice that trace is 0. Summation of diagonal elements is 0, 1 minus 1.